In our last lecture, we had discussed about the discrete Fourier transforms, and there we had seen the mathematical expressions for the normal discrete Fourier transforms as well as the DFT as expressed in the unitary transformation form. We saw the transform pair, that is to say the direct as well as the inverse transformation. Now basically the discrete Fourier transform is, as defined by the transformation matrix itself, it is a complex transformation. All the elements of the DFT matrix, okay, that's a complex one, and as a result, even if we have a real two-dimensional sequence given by UMN, then that results in a complex two-dimensional sequence V of KL when we transform the image using the DFT. Now we had also seen in the last class that the usual computational complexity is of the order of n square by n square, and this can be transformed really into a fast Fourier transform algorithm. That is to say that we can first operate on all the rows, okay, that is to say we take the samples over the columns and perform the DFT for each row, and thereafter we can perform the DFT column wise, and each of these operations, okay, can be done in complexity of n log n. That is to say that the total complexity which we have in the entire DFT computation is of the order of n log n, okay, and the first Fourier transform method, okay, really gives us a fast way of computing the discrete Fourier transforms of two-dimensional sequences. Now today we will be studying some properties of the DFT. Okay, before we go into that, I wanted to tell one thing in the connection of what we discussed in the last class. We had said that we had first transformed the elements column wise, and then we had transformed row wise. Actually speaking, the choice is entirely left to us, okay, by just just by a similar arrangement. One can do first the transformation over the column, over the rows, and then one can do the transformations over the columns. It is just whether you take the WKL term outside the second summation, or whether you take the whether you take KM term or whether you take the LN term outside the second summation, okay. Based on that you have to do either first row then column or first column then row, okay. So we will see some properties of the discrete Fourier transforms today. Now take the discrete Fourier transform expression, okay, which we have, that's to say in the unitary transform form we have the following pair of equations. VKL is equal to 1 by n summation m equal to 0 to n minus 1 summation n equal to 0 to n minus 1 u of mn w to the base n km plus ln, where k and l lie between 0 and capital N minus 1, and the reverse transformation is umn equal to 1 upon n summation k is equal to 0 to n minus 1 summation l is equal to 0 to n minus 1 v of kl w to the base n minus km minus ln, and mn lie between 0 and n minus 1. So these are the transformation pairs, okay, that we have. All right, and basically this u of m, u of mn is the image, okay. It is in the image domain, that is to say it is in the spatial domain, right? And what we have in the transformation matrix is w to the base n and raised to the power km plus ln, and yesterday I had defined w to the base n And what is that? That is exponential to the power minus j 2 pi by capital N, where capital N is the length of the sequence. So really speaking, this exponential term now I can write as a cosine term, cos of 2 pi by n, okay, plus j of sine 2 pi by n. Alright, because I am just expressing the complex exponential as a real part and the imaginary part. Now you see that individually this sine and the cosines, okay, which I have indicated over here, okay, these are indicating waveforms which have got a frequency equal to n, okay. After n, okay, really speaking, if I have this expression as 2 pi multiplied by something, let's say 2 pi omega if I have, okay, in that case when omega is equal to n, that time we have the entire sequence just repeats itself, so that this n really indicates the frequency. Alright, this n indicates the frequency. So what we have after transformation like this, okay, when we transform the original image sequence by this operator, okay, what we get in terms of k and l are the frequency components, okay. So umn was in the spatial domain, whereas v of kl is in the frequency domain, okay. Now in the context of Fourier transform, it is easy to talk about the spatial domain and frequency domain, whereas in general one should always talk about the spatial domain and the transform domain, but in this case transform domain is same as the frequency domain. So what we get from VKL are the various frequency components. Anyway, so now by looking at this expression, okay, the direct transformation as well as the inverse transformation, okay, if we now say, okay, if we now try to compute V of k plus n, l plus n, okay, take this expression, okay, V of k plus capital N, l plus capital N. If I make that, okay, then can you tell me that what results, okay, in this expression? Simply VKL, okay, because whenever I am substituting k plus capital N for k and l plus capital N for l, okay, here k plus capital N, here l plus capital N, okay, then because this is multiplied by exponential to the power minus j 2 pi by n, okay, what we have, okay, as the exponential term is some integral multiple of 2 pi, which means to say that it is the same as this VKL. So VK plus n, L plus n becomes same as that of VKL, okay, and this must be true for all k, all L. What is the physical significance of this equation? The one which I just now wrote? Yes, the frequency domain function which I get, okay, is periodic, okay. What about the spatial domain function? Let us see. Let us take u of m plus n and we take u of small n plus capital N, okay, and try to substitute small m plus capital N and small n plus capital N into this equation. What do we get? We get same as u of mn. So this is equal to u of mn, okay, and that is true for all m, all n. All right. So what we get is a periodic spatial domain function. All right. So both the spatial domain function as well as the transform domain function, they are periodic. So the first property which we study for discrete Fourier transform, okay, is the property of periodicity. Alright. Now the second property, okay, again whenever we are studying any property, okay, we will again and again refer back, okay, to the transformation equations, okay. Now let us look at the transformation expression and we try to see the second property. What we take is that in the frequency domain, okay, we take the sample, okay, as indexed by n by 2 plus k and n by 2 plus L. We are considering this sample, okay. Let us physically interpret this. Actually, instead of drawing a two-dimensional function, let us consider a one-dimensional function like this, okay. Supposing I am considering a function just v of k, okay, where k is varying from, this is k equal to 0 and this is k equal to n minus 1, and here I have n by 2 minus 1, that is to say exactly the middle point. That is to say that the vk samples, okay, will be somewhat distributed like this, okay, and I take the n by 2 is in the middle, so n by 2 plus k means, okay, I have moved by a distance k, okay, over here, okay, and this is just extended in two dimension. V of n by 2 comma n by 2 would have been the pixel at the middle, okay, and I am just moving by a distance of k, okay, in the k direction and by a distance of L in the other direction, okay. So I am considering the transform sample n by 2 plus k and n by 2 plus L, okay. Now if you substitute n by 2 plus k and n by 2 plus L for k and L in this equation, okay, you will find, I leave it to you as an exercise, you will find that this becomes same as V star, okay, the complex conjugate of what? Of n by 2 minus k, n by 2 minus L, alright. So that means to say, again with reference to the one dimensional signal, if I take the sample n by 2 plus k over here, that becomes same as n by 2, the sample n by 2 minus k, but after taking its conjugate, okay. So in one dimensional form it would have been V of n by 2 plus k would have been equal to V star n by 2 minus k, alright. Now very similarly, if I had not taken, okay, n by 2 plus k and n by 2 plus L, if I had taken n by 2 minus k and n by 2 minus L, alright, I would have got that to be equal to V star n by 2 plus k, n by 2 plus L, alright. So this property, okay, is naturally, it is indicating what? It is indicating a symmetric property. But mind you, there is one thing which I must tell you, this expression, okay, is valid only for real sequences. When UMN, okay, is a real sequence, then only this property will be fulfilled. I repeat, when UMN is a real sequence, it is true for images because image means it is a real sequence, real two-dimensional sequence only. When UMN is real, then we are having this complex conjugate property, or rather this second property which we have just now seen is known as the conjugate symmetry property. Okay. The first one was periodicity, the second property is the conjugate symmetry. All right. This you can verify from the original expressions itself. All right. Now, coming to the third property. To derive the third property, okay, what I do is, okay, I take, okay, the sample VKL, okay, but not exactly the sample VKL, okay. I give a shift or a translation of minus K0, okay, to this sample and minus L0 in the L direction. So, what I am interested in finding out is the transform of Vk minus K0 L minus L0, okay. Now, naturally the transform of Vk results, Vkl results in U of Mn. If I assume that, means I know that V of Kl and U of Mn, they are nothing but the transformation pairs. Usually the transformation pairs are indicated by this symbol, okay. A symbol like this, okay, indicate the transformation pair. So, VKL and UMN, we know they are transformation pair. Now, if I consider Vk minus K0, L minus L0, all right, then what results, okay, what is the transformation pair for this in terms of UMN? All right, what happens is that because the term is K minus K0 and L minus L0, okay, you can see from this expression itself, instead of K and L, I will be writing here, sorry, I mean if I do it like this, okay, on this expression, then instead of KL, I will be writing K minus K0, L minus L0, all right, and I will be substituting here K minus K0, L minus L0, and this K0M and L0N, they become a single multiplication constant, okay, a single multiplication term, okay, results over here, okay, and we get the expression like this, that is Vk minus K0 and L minus L0's transformation pair is U of Mn exponential to the power j 2 pi K0M plus L0N divided by N, okay. This we can directly get, okay, from the from this equation itself. I just take substitute here Vk minus K0, L minus L0, and we will get this expression directly. So, it is the DFT of UMN exponential to the power j 2 pi K0M plus L0N by N. This is very simple actually. What I have to do now, K minus K0, L minus L0 means this is K minus K0, this is L minus L0. So, simply that I mean K0M and L0N term which I get, okay, has to be taken out, and this U of Mn exponential to the power j 2 pi K0M plus L0N, that term remains, alright. And very similarly, when I do a translation in the spatial domain, okay, a very similar thing results, M minus M0, N minus N0. If I take this, can you tell me what is going to be the transformation pair of this? V of KL exponential to the power minus. In this case it becomes minus because the transformation matrix itself, its element now become minus because it's complex conjugate. So it is minus j 2 pi. What is that? K m0 plus L n0. Okay, this divided by n. Okay, is the transformation. So this is called as the translation. So that means to say, I have given a shift in the image, okay, and its transformation now becomes like this. Now let us see some very interesting property. If I take the magnitude part of u m minus m0 n minus n0, what happens? Magnitude part is same as VKL, okay, rather magnitude of u m minus m0 comma n minus n0, okay, is equal to or is having the term VKL. I mean its transformation is VKL, because very simply this exponential term that corresponds to the phase. Alright, this is contributing to the phase. So the magnitude part is this one. So the magnitude of, or rather the DFT of mod u minus u m minus n0 n minus n0 is nothing but V of KL. So that means to say that by applying a translation on the image, okay, the magnitude of the Fourier spectrum, okay, of the Fourier transform does not change. Is it clear? Alright, because it is simply, I mean I am not considering this exponential term anymore, because that contributes to the phase angle. Alright, any questions? Pardon? Mode of DFT, sorry, yes, correct. So I should have written this as the magnitude part of DFT u m minus n0 n minus n0, the correct way of writing this should be, is equal to the DFT of u m comma n. Okay, their magnitude remains the same, their magnitude remains unaltered, okay, by applying the translation. Any further questions, doubts? So this third property which we have just now seen is the property of translation. Okay. Now one very important and interesting result from this one, u m minus m0 n minus n0 is having the transformation pair with VKL multiplied by this exponential term. Now when m0 becomes equal to n by 2 and n0 becomes equal to capital N by 2, so I am considering u of m minus capital N by 2 n minus capital N by 2. What am I trying to do there? I am just translating that image, okay, whose origin was in one of the corners. I am just shifting the origin of that image. I mean if the origin was somewhere over here, okay, with this point as m equal to 0, n equal to 0, now I am shifting the origin of the image to m equal to n by 2 and n equal to n by 2. So this is the, so there is a shift of origin, okay, in the original image itself, and when I have m minus n by 2, small n minus n by 2, just substitute, instead of m0 write capital N by 2, instead of n0 write capital N by 2, you already have n over here, okay, and what you get, okay, is simply, I am writing over here and you just verify, its transformation pair is minus 1 to the power m plus n u of mn. Sorry, when I have okay, when I have u like this, okay, then its transformation pair will be minus 1 to the power k plus l vkl, okay, and when I am considering v of k minus n by 2 l minus n by 2, okay, its transformation pair will be minus 1 to the power m plus n u of mn. Alright, so this you can simply get by substituting n by 2, okay, k is equal to n by 2 and l equal to n by 2 in this expression, you get this, and by substituting m0 equal to n by 2, n0 equal to n by 2, you get this. It is minus 1 to the power k plus l, because simply m0 is n by 2, m0 is n by 2, so what remains is k and what remains here is l, okay, and it is, since it is n by 2 and n over here, it is j pi k, and that results in this term minus 1 to the power k, and minus 1 to the power l is contributed by the other term over here, and we get minus 1 to the power k plus l v of kl. Is this clear? Okay. Now, so this property is very interesting and useful, because many a times we would like to shift the origin of the image, or at least the origin of the transformed image, okay, so that the k00 point, really speaking, the frequency spectrum corresponding to k, v00 point, when k is equal to 0, l is equal to 0, we would like to see that point at the middle of the transformed picture, okay, and if we want to do that, this is the transformation that we have to apply on the result. Is this clear? Okay. Now, coming to the next property, okay, let us consider the DFT of summation of two sequences. I take the two sequences, two image sequences as u1 m comma n plus another image u2 m comma n, and I take the DFT of this, okay. It is obvious from the definition of the discrete Fourier transform expression itself that this is equal to, can anybody tell? So DFT of sum becomes equal to sum of DFTs. Rather, this is equal to DFT u1 mn plus DFT u2 mn. Alright, and this is the distributive property, distributivity I can say. So this is the property of distributivity, okay, that I have the DFT of sum as the sum of DFTs. Now I can consider an image, okay, where I have made some scaling in the spatial directions. The spatial directions are m and n, and in that I am doing some scaling. So that is to say, instead of taking the image as u of mn, I am considering the image u of am comma bn, where a and b, okay, where a and b are some scaling constants. A and b are scaling constants. If I take that, okay, then its corresponding DFT, okay, is given by 1 upon mod AB, okay, V of K by A, L by B, okay. So this is the scaling property. So what happens whenever I am multiplying, so it is very interesting to see, whenever I am multiplying by a constant in the spatial domain, in the frequency domain, it becomes a division by the same factor. I had got AM in the spatial domain, and in the frequency domain I am getting K by A. In the spatial domain I have got Bn, in the frequency domain I have got L by B, okay, and an overall normalization factor 1 upon mod of AB, okay, has come about. So this is the scaling property. So together I can call this property number 5 as distributivity and scaling. We will now consider the relationship between the average value of the pixels in an image with the 0,0 components of the frequency. That is to say, in VKL, when K is equal to 0 and L is equal to 0, it is very much related with the average intensity, and let us see that. Now the average value, I am writing UMN U bar, okay, indicating the average, and that is equal to double summation of UMN, where M is equal to 0 to n minus 1 and n is equal to 0 to n minus 1. So this gives us the summation of all the pixels in the image, and this has to be divided by 1 upon n square. So 1 upon n square times summation m equal to 0 to n minus 1, n equal to 0 to n minus 1 u of mn gives us the average value, okay. And now we have to relate this to the frequency component V00. Original DFT expression, okay, and then see that what is V00. Substitute for K and L, okay, in the original DFT expression, okay. What are you getting? Can anybody tell me? Pardon? Average value directly, or the little bit of difference in the normalization factor. V00, if you are substituting in the DFT expression, the normalizing factor is 1 by n. The unitary DFT expression you take, so that it becomes 1 upon n summation m equal to 0 to n minus 1, summation n equal to 0 to n minus 1, okay. And what is the term written over here? Simply u of mn, because the complex term becomes equal to unity, because I have got the indices as 0, 0 simply, alright. And this is equal to what? This is equal to, okay, 1 upon n square of this is the average value, okay. So this is, I can say, n times the average value u of mn, okay, or rather the average value u of mn is nothing but 1 upon n V00. So simply what I get is that the average value of the image is equal to the very first frequency component. The very first frequency component is V00, and this becomes same as the average value. You remember, in the one dimensional sequences, the average value of a randomly varying signal, okay, the average value is given by the very first component of the Fourier spectrum, okay, and that we call as the DC value. So in this case also, whatever we have got is equivalent to the DC value of the image. Okay. This is the very first frequency component. Okay. And as you increase, I mean V00 is giving you the DC value, and as you keep on increasing the indices K and L, okay, you are going over to, from the DC, you are going over to higher and higher frequency components. When K and L are high, okay, that means to say we are considering the higher frequency components, and when K and L are low, we are considering the lower frequency components. So, the DFT coefficients, or rather the transformed image coefficients VKLs, okay, they directly give us the frequency components, which I had explained in the class itself. Okay. So, this is our sixth property, or rather relating the average value to the relating the average value to the V00. Now, another important property we see, okay, that is the property of image rotation. We have seen the effect of translation, okay, that is to say shifting of origin, okay, on the Fourier, on the DFT, okay, we have seen its effect on translation. Now we are seeing its effect on rotation. So, in order to study the rotation, okay, what we are doing is we are just transforming from the mn coordinates, okay, to the polar coordinates, or rather the Cartesian, from the Cartesian coordinates we will simply go over to the polar coordinates. Okay. So, in the spatial domain whereby indices were m and n, okay, I write it as m, I write as r cos theta, and n I write as r sin theta. Okay. So, that r theta is the polar coordinates in the, this is polar coordinates in spatial domain. Okay. And very similarly, we say omega phi as the polar coordinates in frequency domain. So, how is omega and phi related to k and L? K is equal to omega and phi are the polar coordinates in frequency domain, and k and L are the Cartesian indices in the frequency domain. So, simply k is omega cos of phi and L is equal to omega sin of phi. Alright. Now, if you are taking this substitutions, okay, again it is very easily verifiable, and I leave it to you. Okay. You can show that u of r theta plus theta 0, that means to say, now instead of writing it as u of mn, I am writing as u of r theta. In terms of the polar coordinates, I am writing as u of r theta, but instead of theta, I have given it a shift of theta 0. Okay, that means to say a translation in the theta domain, rather giving it a rotation. Alright. So, u of r theta plus theta 0, okay, its transform pair is, it is very interesting, v of the transformation pair of u r theta is v of omega phi, and the transformation pair of u r theta plus theta 0 is v omega phi plus theta 0. So, if the original image, okay, is rotated by an angle theta 0, alright, then its corresponding frequency spectrum, okay, is also rotated by the same angle theta 0. Alright. So, this is the property of rotation for DFT. Okay. You can verify this in the expressions for mn KL, you just substitute these expressions, okay, and you will get this result. All right. Now comes a very important, very important and a very interesting property of the discrete Fourier transform, and that is the property of convolution. So this is the 8th property, or this is the property of convolution, or what we will now define is the property of circular convolution. I will first define what the convolution is, because later on in our course we will be very often using this term convolution. So I will try to give a simple mathematical as well as a physical definition of this convolution. Now let us take two sequences, okay. One sequence I am calling as u1 m comma n, a sequence u1 m comma n in the spatial domain, okay, and I take yet another sequence h of m comma n, okay, a second sequence. Now in general I am assuming that u1 of mn and h of mn, okay, these two sequences differ in size. So that means to say, if I consider the mn space like this, supposing this is the m direction, this is the n direction, and I assume that the image, or rather the u1 of mn, okay, is defined within the range of 0 to n minus 1 in m direction and within the range of 0 to n minus 1 in the n direction. So u1 of mn is really an n by n image. So this is of size n by n, and the second sequence h of mn which I have got, okay, I define that that is a shorter sequence, possibly a sequence like this. All right, this is the sequence h of mn, h of mn, okay, which is defined over 0 to m minus 1 and in m direction and 0 to m minus 1 in the n direction. All right. Now the definition of circular convolution, okay, as defined mathematically is like this, okay, and then I will give you the physical interpretation. Okay, before that I take it this way, that when the function h of mn is within this zone which I have indicated by this shaded region, when it is this zone, then hmn is not equal to 0, whereas when it is in the unshaded portion, okay, in this range h of mn is equal to 0. So simply I have taken two sequences of unequal lengths. One sequence is of size n by n and the sequence h of mn is of size m by m. And now I will give you the mathematical definition of this. Now the convolution, the circular convolution as defined mathematically is like this. It results in another sequence given by u2 of mn, okay, which is defined in terms of the two original sequences h of mn and u1 of mn like this. We take not the signal h of mn, rather we take h of m minus m prime, comma n minus n prime, okay, and I put a symbol C over here because I was calling circular. Till now I haven't defined what that circularity means, okay, and u1 I am having indices instead of mn, I am writing the indices as m prime n prime, okay. I will tell you the purpose that why I am using m prime n prime and not mn, okay, and the summation expression, okay, the summation is to be done in a two-dimensional way. The summation is defined as m prime equal to 0 to capital N minus 1, n prime equal to 0 to capital N minus 1. Okay. And let me now define what is H m comma n c. What does this circularity C means? It is simply H of m modulo capital N comma n modulo capital M. So it is the same as H m n c is same as H m modulo n comma n modulo capital N. You know what is modulo n. So that means to say that if I have H of mn, okay, where the value where the indices m and n they exceed capital N, okay, in that case it just folds over. That means to say that if I consider the sample H H n plus 1, okay, n plus 1 if I consider, then really speaking I am considering the pixel H11, okay, because it is modulo n, okay. So H m modulo n comma n modulo n, this is defined as the circular function. So H is now a circular function, but what is interesting to note is that the indices I have just changed from m to m prime n prime, okay. So for u there is no problem, u of m prime n prime, okay, is there, but when it comes to H, okay, I find that I have done something interesting. The m prime and n prime which was there, okay, has now become minus m prime and minus n prime, okay. Let us physically draw what I tried to do. I have gone over to a, as if to say I have gone over to a new coordinate system, okay, which I am calling as m prime n prime, okay, and my image, okay, u1 is defined by m prime comma n prime, okay, in this zone, okay, and I have considered the function, okay, which was originally H of mn was like this, and now let us consider the function H of minus m prime minus n prime. How should I draw this function? My H of mn was like this, and I want to draw H of minus n, or rather H of minus m prime minus n prime. I have to just fold over this function. So that means to say that whatever I have drawn like this, okay, I should now draw, okay, like this, a folded function of this form. Whatever I have drawn within this orange boundary, I am going to draw the, consider the function in this form. Alright. So that means to say what? That whenever I am considering simply the function H of minus m prime minus n prime, it is this function, this HMN function folded over in both m and n direction. But I have not considered minus m prime minus n prime, rather in my expression I have considered H of m minus m prime n minus n prime, okay. So that means to say that I have taken, or I have shifted the origin of this particular function to the point mn, okay. So I have considered the function of this nature. This function when I translate, okay, to the point mn, okay, the function will appear like this. If I extend my m prime axis and n prime axis, it is this, okay, and this is the point mn where I have shifted the origin. So what I draw now, okay, in this region, okay, is nothing but my function H of m minus m prime n minus n prime, when I am drawing this, okay, on the m prime n prime coordinate system, okay. And now what I am considering, this particular function, okay, after being folded over is to be swept over this entire image, entire image space covering all M, covering all N, I will sweep it over, okay, because in my mathematical definition it is said M prime equal to 0 to N minus 1, N prime is equal to 0 to N minus 1. So that means to say this I have to sweep over this entire range, and after sweeping over the entire range, for every such position, I mean I have to keep on shifting this over the entire image space, and for every position what I have to do? I have to do a multiplication with the original image U1. So together what is called, okay, this operation is called as the convolution. So it is nothing but folding a function, okay, and then sweeping it over the entire image space, okay. Now because it is circular convolution, okay, see what happens to it, okay. I am considering now, I mean as long as it is, I mean I am considering this part of the h function, okay, this is getting multiplied by this zone, okay. But what about this? Not 0, okay, because it is a circular convolution. I have not considered h m minus m prime n minus n prime alone. I have considered h m minus m prime n minus n prime c. C means m modulo n modulo n. So where will this part go? Let me draw this with a green pen now. Where will this green part go? The green part will now appear, okay, on the top, because it is n prime modulo capital N. So the green part will go over here and get multiplied with this, okay. Now, okay, now this portion, okay, will get transferred over here, and the last portion, okay, that means to say this black region, okay, will appear over here. So what I will have in the image when Mn is in this position such that, okay, this h of m minus m prime and n minus n prime, this indices m minus m prime and n minus n prime, they are exceeding the image, okay, then I will be considering the modulo function of this, and after considering all these different portions, okay, I have to do the multiplications and add it up, and that operation I have to do over the entire pixel range. So this was only for one particular position, but this function is to be swept over the entire range, and this is the concept of convolution. Now as you clearly see over here, the convolution in this case is its order of complexity is n square, okay. Now convolution, we have to do it like this. It's a bit complicated in the sense that we have to fold over the function and then sweep it over the entire range, okay. We will see, okay, in the next class. We will spend some time first to indicate that whether we need to do the convolution like this, or we can do some simplification in the frequency domain, okay. Frequency domain means if we take, so now what we will attempt to do is we will take the DFT of U2 Mn, okay, and we will see what results, okay, in this right hand side, okay. Any questions?
M prime and n prime.
What is U of n prime and n prime?
What we've done to h of m minus n prime. We can do the same.
Exactly. The same thing can be done, the same convolution could have been done on U1 also, okay. But generally the convolution is done on the shorter sequence, okay, because h of mn is assumed to be a shorter sequence, that is why we are doing it on this. Let me tell you a simple application of this, since you have brought about. U of Mn is the entire image space, possibly a 256 by 256 or a 512 by 512 image space, okay. Whereas H of Mn is typically, it is a filter size, and a filter size is usually smaller, okay, maybe of the order of a 3 by 3 or a 5 by 5 pixel, okay. And if I want to do the filtering operation, okay, in the spatial domain, okay, I have to do this kind of a convolution, okay. But we will see that if we want to do a filtering, okay, by the convolution operation, the convolution filtering operation, if I want to do in the frequency domain, what do I have to do? Okay, we will see it in a minute. Translation property, yes.
Is it periodic shift or circular shift?
Is it
Periodic shift or circular shift?
translation? Well, I mean, it results in a periodic shift. Okay.
But this limit signals are only finite length signals.
Correct.
How will you get to the periodic shift?
Well, the thing is that whenever you are taking finite number of samples for a function, okay, like U of Mn, U of Mn is what? Is the sample of the image, okay, and you have taken the samples in the range n equal to 0 to n minus 1, n equal to 0 to n minus 1. Now once you have taken the sample, you are restricting the entire image space to that, okay, but if you are considering the extensions of this function, okay, it results in a periodic signal. So once you sample it within a particular range, okay, the extended U function which you are taking is a periodic U function. So that is to say that whatever you have, U m n, n and n in the range of 0 to n and 0 to n, okay, it becomes a periodic function when extended. Okay. So we are assuming that the components, the U of Mn which are non-existent, okay, they are not zeros, rather they are the repeated, or rather the periodic components which we are taking. Alright.